Hello class, this is CSE-5720, Section 2, Week 11, Fall 2025. Alright, so, we're gonna get started on our discussion on Chapter 8, but we're also gonna go over the answers to homework number 2. So, let's look at homework 2 first. So, let me pull that up real quick. So, there were 8 queries that I had you answer for homework 2. And here are the solutions for that. So, 1A. Oh, and by the way, what I really should have done for that assignment was give you all the tables necessary to answer all the queries. But there was actually one error that I discovered way too late. And that was, there should not be a relation called course department. What actually happened is this. Course department only existed in the ER diagram. So, that information would have been merged into just the course relation up here. Since this is still the same exact information, since course and course department contain all the same information as this course relation here, the queries that you're gonna be writing are still valid. It's just that you're gonna be writing them a little bit differently. It's like you only are using the course department relation for like 1 or 2 queries anyway. So, yeah, don't worry about this mistake. It's all the same information anyway, just broken up into one too many tables. But we're gonna wrestle with that when we get to the first query. That is, find the name of all students who have taken at least one computer science course, and the result should have no duplicate names. So no duplicate names means we need select distinct name. From what table then? Well, here's the solution that I talked about in class. From student natural join takes, where course ID like CS, and then the percent is a placeholder for the rest of the string. So select distinct name from student natural join takes, where course ID starts with CS. That's the naive solution. So let's look at the tables for that to see how that works. So the tables were student and takes. Here's student. And up here is takes. So a natural join is performed between these two, and it's going to match up all the students with all the courses they've ever taken. We find the course IDs that start with CS. And then we find all the unique names that corresponds to those classes taken. And that's how we find all the names. The names of all unique students who have taken at least one computer science course. If they have at least one, if a student has taken at least one course whose course ID starts with CS, that is a student who has taken a CS course. Their name is reported in the result of that query. So I've also been tipped off to a more robust solution, which is based on nested queries. So the innermost query, select course ID from course department where department name equals computer science. That finds the course ID, it finds the course IDs that correspond to computer science using the data in the course department table. So this is where the hiccup I was talking about is coming up now. There is actually no course department table in our example database. So actually all that information exists within the course relation, whose attributes are course ID, title, department name, and credits. Problem is, when I wrote that here, I accidentally ended up splitting it into two. So course and course department should really be joined together into one table. But course department contains the two things we need, department and course ID, but so does course here. So if you're able to figure out that is that department name and course ID matched together here. So if you just ignore the title and the credits here, that's basically all the information in the course department table that doesn't really exist. what it's doing is mapping all courses by course ID to their department. So here are all the CS classes. They belong to the CS department. So that's what that innermost query is doing. It is mapping all the computer science course IDs to the department name of computer science. So now we have a list of all the courses that belong to the computer science department. So that's what the innermost query is. Select ID from takes where course ID is in that subquery. Select ID from takes. Okay, so we have a list of so we have a table that contains all the computer science courses. We're gonna find the IDs of students who have taken a computer science course. Okay, so we're just gonna see whether any of these entries in the takes table contains a course ID that corresponds to the computer science courses in here. And now once we have those IDs, and there may be duplicates, but select distinct is gonna take care of all those duplicates. Now we have that list. Now we have that table of IDs. Now we can perform the outermost query. Select distinct name from student where ID is in that list of IDs from that subquery. So that subquery has all the IDs of students who have taken computer science courses. So we select the names of all students whose ID appears in here that corresponds to a course ID that appears in here that corresponds to a computer science department course. You see where this is going? The innermost query finds all classes associated with the computer science department. The middle query selects the student IDs for anyone who has ever taken a computer science course. And this query out here, the outermost query, finds all the names of those students who have taken a computer science course. All the unique students. So select distinct name from student where ID in subquery down here. So that's it. This is a more robust solution because, the naive solution assumes that we are writing all our computer science courses like this. And if we fail at maintaining this notation, if we fail at writing all the course IDs for all of our computer science classes like this query will fail. But assuming all computer science classes are written like this, with CS at the start of the course ID, then the naive solution will work. This is just a more robust solution because just in case we write a computer science course ID differently from CS dash such and such number. So that's solution number 1. Solution number 2, find the name of all students who have never taken a computer science course. So an easy way to do that is to just take the solutions for number 1 and just invert the logic. So one solution is select distinct name from student natural join takes, where course ID is not like CS at the beginning. That's one way to do it. If you wanted to go the nested query route, we can do select distinct name from student natural join takes, where ID is not in. And check this out. This is just a modification of this query, but we're not selecting distinct name. Rather, we're selecting ID. So select ID from student natural join takes, where course ID is like CS at the beginning. So this returns the student IDs of everyone who has ever taken a computer science course. What this query is doing is finding everyone who has never taken a CS course by seeing whether they are not in this table. And there is a solution that is based on the robust one over here. Select distinct name from student where ID in the subquery here. We're gonna invert the logic for that one where ID not in the subquery. So the robust solution is a query in a query in a query, where the outermost query is testing for membership, where ID in this subquery. If we want to find all the students who have never taken a computer science course, we swap where ID in subquery. We swap that for where ID not in subquery. So once you solve number 1, you have like 90% of the solution. Yeah, so once you solve part A, you have 90% of the solution for part B. Alright, so let's move on to parts C and part D. For each department, find the maximum salary of instructors in that department. So select department name and max salary. When I talked about this in class, I forgot to put the department name, and we actually need that so we can tell which salary is which. So select department name and max salary, as we have to alias it. It's a good idea to alias it so we know, so that way we have attribute name for this maximum salary. So select department name, max salary as max salary from instructor, group by department name. So group by department name, we're gonna find the maximum salary of each department. So that's part C. Part D says, across all departments' maximum salaries, find the lowest of those maximums. So that would be select min max salary, and this is why we have to alias it as lowest max salary from subquery from part 1C as department max salaries. It turns out, depending on the implementation, you may need to alias this subquery here. I just added in here just to be safe. Yeah, every implementation of SQL may do something different from one another. I went ahead and cross-referenced this from, I cross-referenced the solution to make sure it was correct, and yeah, some implementations of SQL may or may not require this as department max salaries. So select min max salary as lowest max salary from subquery from part 1C as department max salaries. So part C and D, they build off of one another. So once you have the solution for part C, you have like 90% of the solution for part D. So question 2 part A, create a new course called CS001 called Weekly Seminar, and it's worth 1 credit. So we just have to insert into course, course ID, title, credits, and the values for that tuple are CS001, Weekly Seminar, and 1. That's it. Part 2B, create a new section for CS001. We have the section, no, we have the course, but we need to make a section for it. Create a new section for that class with a section ID of 1, and it's in fall 2009. Insert into section the tuple course ID, section ID, semester, year. Values CS001 as the course ID, 1 for the section ID, fall for the semester, year is 2009. There we go. So these don't really build off one another, but they are nearly identical to one another. What we really want to make sure is that these attributes here line up with these attributes. So there's several ways to insert new tuples into a relation. This is just one of several ways. So there's several ways to write this, and this is the most straightforward way. In case you don't know what the attributes are, or the order they were supposed to be in. Parts 2C and 2D is where they build off one another. Again, so part C, there are a few solutions to this, and one possible solution involves the limit keyword. We don't need to do that if we are assuming that no students are ever going to be tied for the highest number of credits. And since we are going with the maximum, since we're using the max aggregate function, there's only going to be one possible student at the top anyway. So part C is find the computer science student with the highest number of credits and add that student as an instructor. Assign that student a salary of $30,000. Assume no students are going to be tied for the highest number of credits, and when we add the student as an instructor, they don't get deleted from the table of students. So this is just one possible solution. Insert into instructor, ID, name, department name, and salary. And when we insert into a table like this, we can insert the result of another query. So we're going to insert into instructor the result of this query here. Select ID, name, department name, and 30,000 from student, where department name equals computer science, and total credit equals the max total credits of all computer science students. So this query here, that is a query that returns a 1-column, 1-row table, and all it contains is just the highest total credit of all credits of all computer science students. So if this student's total credit equals this, the highest credits of all students, we're going to end up returning this subquery is going to return the student with the highest number of credits, and they're going to be assigned as an instructor. Once we have this, we have 90% of the solution for part 2D, which is this. So part 2D, assign the student from the previous query to teach section 1 of CS-5720. So use the result of the previous query. All we really need is this, and we just gotta modify the attributes in the select clause. So insert into teaches ID, course ID, section ID, semester, and year. We have to select the student ID corresponding to the student with the highest credits. Select ID CS-001 fall 2009. So this is the ID of the student who has the highest credits. Everything else is just attributes that we have to pass in. So we have information for the course ID, section ID, semester, and year. Select ID and all this from student where department name equals computer science, and total credit equals the maximum total credits of all students who have ever taken a computer science course. So yeah, that's all 8 queries asked for in homework 2. There we go. Hopefully this is all straightforward. If your answers are close enough to these, I will take that as a result. And then, once again, I really should have just given you the tables from the get-go. But also, my apologies for giving you a table that didn't exist in our running example. But once again, it's close enough that, yeah, so course is actually just these 2 schemas combined. So yeah, that was an oversight on my part. But it does contain all the information that we otherwise need, just broken up into one more table than we really needed to work with. Alright, so that is the solutions for homework 2. Let's look at chapter 8. Okay, so chapter 8 is relational database design. We started with chapter 7, but now we are moving back to, we're gonna move back forward in the book and talk about chapter 8. So, in chapter 7, we talked about drawing an ER diagram to represent an enterprise, and the goal is to do so without unnecessary redundancy and also allowing easy access of data. In general, this is the goal of relational database design. And doing so requires designing schemas in an appropriate normal form. We're going to talk about normal forms. So what are some good features of a good database design? Well, we can start with the ER diagram and then create a set of schemas from that. We can use that as a starting point of our discussion. But the schemas that we make this way are only as good as the diagram from which they came from. Later we're going to be more precise with assessing whether these schemas are good. But before we do that, let's look at a few design alternatives. Let's look at the first of these alternatives, and that is having large tables. What if we combined the instructor and department tables into one? Then we get a table that might look like this: ID, name, salary, department name, building, and budget. So this is a combined instructor and department table. It has the advantage of, if we ever need to do anything with both instructors and departments, we don't need to do a join operation between these two, since, well, it's already joined for us. But the benefits of that are outweighed by the disadvantages, and these disadvantages are something we've talked about even early in the course. We have redundant data, and then we also have the risk of inconsistent data. And most glaringly, we can't represent departments by themselves. For us to talk about a department, we must also be talking about an instructor. We can't easily represent departments on their own. They're their own entities. They should not be connected to a instructor to exist. So, we can add new instructors by adding null values, but eventually that instructor is going to be associated with the department. So here's the problem: we can't represent departments on their own. We can in a rather draconian move, we could eliminate everyone from a department, but the department will still exist in an abstract sense. Getting rid of all the instructors in a department does not destroy the building that the department is in. Nor does removing a department necessarily remove all the instructors. They could just get reassigned to new departments, for example. In either case here, the presence of null values is troublesome. So we can't represent instructors on their own, and we can't represent departments on their own. Also, look, check this out. We have computer science building and budget information repeated. That's not good, because what if we update the computer science budget, but we forget to update one of those copies? This is the risk we have. This is the risk we have when we have computer science repeated like this. This is inconsistent data. If you forget to update all the copies, they're not going to agree with one another. Which one's correct? We can't know. Well, we don't know. So, basically, this design is problematic. And when we create our ER diagram for the university like this, we are going to know that this is problematic. And this would never be made. But what if someone designed a database for our university example, and then they just created a table like this? What if this is something we had to start with? How would we recognize that it had to be split into two? Well, a naive approach would be to just look for repeated data. Although this is doable for this small example, in practice, databases may have thousands, maybe millions of tuples. So this method of just looking for repetition is unreliable. Another problem is this. How are we so sure that having 3 instances of computer science is not a coincidence? So it turns out this is something that we just can't answer by looking at the tables. Rather, it's something that we can only answer by looking at the enterprise. So assuming we have a well-drawn ER diagram, we can look at the diagram and realize, okay, so instructor and department, they are supposed to be 2 separate entities. Therefore, we need 2 separate tables for them. Okay, but what's up with that instructor-department relationship over there? So we have instructor and department, and they have their own schemas, but then we have instructor-department over here, and that requires its own schema. What gives? Well, if you recall from chapter 7, that instructor-department relationship, when we create the schemas for these 3 things, if you recall, we go through a simplification process where the information for instructor department just gets merged with the instructor relation. So we don't have a table called instructor department anywhere. It just gets merged with instructor, and that's why the instructor relation contains 4 attributes: ID, name, salary, and department, not just 3. So yeah, this is something that we talked about in chapter 7, the simplification process of merging schemas together. Situations like this don't always occur though. If this is the case, then it's necessary to specify additional rules, such as each specific value of department name corresponds to at most 1 budget. In other words, 1 budget per department name, and the department name is the primary key. Rules such as this, where department name determines the budget, these are called functional dependencies. They are written like this, where attribute, right arrow, another attribute. We read this as attribute determines another attribute. So department name determines the budget. A rule like this functional dependency where the department name determines the budget, it's enough to declare that this table is problematic. Because the department name is supposed to be a primary key. I guess we're not up to primary keys yet, but well, we're just gonna go with the primary key. We're just gonna assume that department name is supposed to be a primary key. Here's the thing though, if we use department name as a primary key by itself, that's not enough information to uniquely identify each row, because look, we have repeated information here, computer science, computer science, computer science. That is not enough information to uniquely identify each tuple in this relation here. So the problem is we want department name to be its own primary key, but we can't. So the only way to do that is to split it into 2. So now department name can be its own primary key in its own relation. So observations like that is enough for us to conclude that this table should be split into 2 tables. This is called decomposition. And we can go too far with decomposition also. So on the one extreme, we have large tables and it's hard to represent data. On the other extreme, we can decompose too far, and let's see what happens if we do that. Here's a decomposition of employee into 2 parts, ID and name, in one relation, and then in another relation, name, street, city, and salary. So, say we have an employee relation like this. We have 2 people named Kim, and they live in 2 different cities, and they have 2 different salaries. We decompose the table into 2 relations, one that contains the employee ID and the employee's name, and another one that contains the name of that employee and the place that they live at, and their salary. When we do a natural join on these 2 relations, which Kim is which? When we do a natural join like this, we don't have enough information to join Kim's information with the right Kim. So the original employee relation had enough information to pair the right information with the right Kim. When we decompose this way, we lost that information. So when we natural join, we don't know which Kim is which anymore. This is called lossy decomposition, which is what we don't want either. What we want is lossless decomposition. So we just had a Goldilocks and the 3 bears situation. On the one hand, big relations are bad because, well, big schemas are bad because, well, it's hard to represent data. But small schemas are also bad because we might lose information through lossy decomposition. So how do we know that a schema is just right? So as I said, on one extreme, we can prevent large tables from being made by having a well-drawn ER diagram. So that's how we can prevent ourselves, this is how we keep ourselves from making large schemas like this, where it's hard to represent departments on their own when they really should be represented as their own thing, separate from instructors. On the other hand, we can go too far with the decomposition to the point where we have information like Kims and we don't know which Kim is which anymore. An ER diagram. When we talked about ER diagrams, there were things called multivalued attributes and composite attributes. Multivalued attributes are like when you have more than one value for a field in a table. Like how some people may have more than one phone number, or maybe more than one email address. So that's a multivalued attribute, when the value for an attribute is not one value, but rather a set of values. A composite attribute, that's basically when an attribute is composed of several smaller attributes. So an address is composed of several parts, for example. You have the street, city, zip code, state, and so on. When we have information like that, multivalued attributes and composite attributes, when we create an ER diagram, that substructure is there, but when we turn it into a set of schemas, that substructure is lost. So the address, in this case, for each component attribute in that composite attribute, it becomes its own attribute. So basically we get a column for each street, city. So we get a column for the street, city, state, and zip code. For the multi-valued attributes, we get a row for each phone number. So, let me repeat this. If we have an address that is composed of several smaller parts, those parts get their own column. If we have people who have more than one phone number, each phone number gets its own row. So that's how we lose that substructure. If, for a relation, each attribute is atomic, that is, we cannot divide it any further into smaller parts, then that relation is in a normal form called first normal form. So these two tables are in first normal form, but this one is not. So, composite attributes, such as an address, are non-atomic. They can be broken down into smaller parts. The street, the city, the state, the zip code, or whatever rules you may have in, say, Canada or the UK or whatever other country there is in the world. Because postal codes, they're called postal codes in Canada, for example. They're only called zip codes. As far as I can tell, they're only called zip codes in the US. There might be another place where it's also called zip codes, by the way. So, an address is not atomic, because you can break it up into pieces. Integer values are assumed to be non-atomic also. However, is a phone number atomic or non-atomic? You may have grown up knowing a 7-digit phone number, and then you had to add on to that a 3-digit area code, and then you may have had to add on to that a 1 or 2-digit country code. So it depends. So depending on the input system for a phone number, you might have to enter those separately, or you just enter everything as one long 10 or 11-digit string. A phone number like this is considered non-atomic if the atomic components, like the area code, are used differently from the rest of the phone number. If not, then splitting the phone number into an area code and a 7-digit phone number, any further than that, if you split the phone number into an area code and a 7-digit phone number, and doing so provides no new information, then splitting it up is not necessary. Splitting it up provides no new information. The 10-digit phone number is considered atomic. This is to say that atomicity is not an absolute property of the data type, but it depends on what we're doing with it in the first place. It depends on the use and the semantics. For example, you might see room numbers like this for, say, a hotel, and it is secretly encoding a floor number and a room ID. So room 1402 really means floor 14, room ID number 2. And then room 0323 secretly means floor number and room ID. Is that information important? Could be. It could be important. Or maybe it's not, and it's just easier to go with the 4-digit room number. So depending on what's going on with this hotel, it may or may not be a good idea to split the room number into a floor number and room ID. For our discussion, we restrict ourselves to relations in first normal form. So we require every domain to be atomic. So here's the main idea of what we're going to get into in this next section here. A functional dependency. A functional dependency is a constraint between two sets of attributes within a relation, where one set of attributes x determines the values of another set y, which we denote as x determines y, or y is determined by x. It's just easier to read it as x determines y. Sometimes x and y are singular attributes, but generally we may be working with sets of attributes. So one attribute might determine the value of another attribute, or we might need two attributes to determine the value of 2 or maybe 3 or 4 or 5 attributes. Before we go, I need to talk to you about the notation that the textbook uses. So, we use lowercase Greek letters to represent sets of attributes that may or may not be schemas. We use lowercase Latin letters, followed by uppercase Latin letters in parentheses, to represent a relation schema. So, little r, and then in parentheses, big R, that is the schema for a relation little r, and big R is the set of attributes. If the name of the relation doesn't matter, we can just call it big R. If we have, we have lowercase Greek letters for sets of attributes, and then capital Latin letters to represent sets of attributes that are schemas. So attributes, so big A, big A, big A, big B, and big C, those are schemas. Alpha, lowercase beta, and lowercase gamma may not necessarily be schemas. They may or may not be schemas. We use capital K to represent the superkey of a schema. Lowercase names are used for the names of schemas. They can describe something realistic, like Instructor, or they can just be a singular letter if we are using that as part of the definition of an algorithm. A relation can have a particular value at any time. To refer to that, we say instance of R. If it's clear that we're just talking about an instance if it's clear that we're talking about a relation instance, we can just call it little r. Oops. Let me move my face cam while I break up my recording setup. If an instance of a relation satisfies all its constraints, it's a legal instance of that relation. A legal instance of a database is one where its relation instances are all legal instances. So there is a formal definition of a superkey in the textbook, but a somewhat informal definition is as follows. For a relation schema R, K is a subset of R, and K is a superkey if it can be used to uniquely identify every tuple from that schema. That was something that we talked about early on in the course. So what's the definition of a functional dependency? Well, a functional dependency lets us express a constraint that uniquely identifies the values of certain attributes. So consider a relation schema R and the attributes subsets alpha and beta. These are subsets of R. So here's the formal definition. Given an instance of R, we say that the instance satisfies the functional dependency alpha determines beta if for all pairs of tuples T1 and T2 in the instance such that T1 alpha equals T2 alpha. It's also the case that T1 beta equals T2 beta. We say that the functional dependency of alpha determines beta holds on schema R if every legal instance of R it satisfies if an you can probably see me struggling with the formal definition. We say that the functional dependency alpha determines beta holds on schema R if in every legal instance of R it satisfies the functional dependency. You want to just see an example of what I just was talking about? So, let's look at an abstract example of what it means for a functional dependency to be a functional dependency. So here is a relation R, and it has 4 attributes A, B, C, and D. Here, A determines C. How do we know? Well, let's look at each tuple. Well, look, we have 5 tuples, and 2 of them have values A1 and C1. Here we are. A1, C1. There are 2 tuples where the values are A2 and C2. And then there's one more tuple where the values are A3 and C2. Here, here, and here. It might be a bit more helpful if we just visualized it as sets like this. So we have values A1, A2, and A3 for our values of attribute A, and C1 and C2 for our values of attribute C. Let's draw arrows so that the values of A1 map to their corresponding. Let's draw arrows so that the values of A map to their corresponding values of C. Remember, there are 2 tuples where the values were A1 and C1, 2 tuples where it's A2 and C2, and 1 tuple where it's A3 and C2. So, values of A map onto values of B such that no one value from A maps to no more than one value in B. This is the definition of a function. It's called a functional dependency because there is a function that maps values in one attribute to another. There are values. It's called a functional dependency because values for one attribute map to only one value in another set of attributes. So A determines C because there's a secret function somewhere that we can define where A1 maps to C1, A2 maps to C2, A3 also maps to C2. It's exactly like a function in math. Is it okay that A2 and A3 map to C2? Yes, this is a many-to-one mapping. It also works if it's a one-to-one mapping, but it doesn't need to be a one-to-one mapping. A one-to-one mapping is also called a bijection. By the way, word of the day, bijection. But anyway, this is a function where every input we can ever give to the function results in one and only one output. So it would not be valid, for example, if C determines A. This is not a functional dependency because C2 splits into 2 values. We don't want that. So this is a one-to-many mapping, and it also doesn't work for our purposes. Many-to-many doesn't also work either. There's also the notion of what is called a trivial functional dependency. A functional dependency X determines Y is trivial if Y is a subset of X. So we have 5 values in X, V1 to V5, and 3 values in Y, where it's V1 to V3. The values V1 to V3 are also in X. X determines Y is trivial because V1 determines itself. That is trivial. If a function is defined as f of x and y equals x, or f of x equals x, these correspond to trivial functional dependencies because if this were a database, these dependencies are always true and they don't add any more information if we add other stuff to it. If I give you $10 and train A is traveling at 50 miles an hour and train B is traveling towards it at 80 miles an hour, how many dollars do you have? The answer is $10. Adding information about the trains doesn't change the amount of money that you have. I gave you $10 and then I gave you extra stuff about the trains. But it does not change the fact that you still have $10. Adding information about the trains does not change the fact that you still have $10. This is what it means to have a functional dependency that is trivial. Oh, for fun, here's department name and budget visualized using this set notation here. Department name determines budget, where each department name has one and only one value for a budget. And this is what it looks like if it were inconsistent. So computer science has two budget values, which is bad, because we don't know which one is which anymore. Let's go back to this. Let's go to this instance here. So this is an instance of the classroom relation where we have building, room number, and capacity. So, can we say that building determines capacity? No, because look at the Watson building. There are 2 rooms in the Watson building, so this would have to map to 50 and 30. That's a one-to-many mapping, which is not allowed for a functional dependency. We want, at the very least, a many-to-one mapping. Okay, but can we say that the room number determines capacity? Well, yes, because look, we can map 101 to 500, 514 to 10, 31 to 8 to 70, 100 to 30, and 120 to 50. That is a one-to-one mapping, which means we can say that this mapping from room number to capacity, room number determines capacity, is a functional dependency. And it works. Or does it? What happens if we add an admin building and it also has a room 101? Suddenly, there are now 2 room numbers and they both map to different values. So room number determines capacity no longer works here. Room number determines capacity. Now we don't have enough information to determine the capacity of each room anymore. So although room number determines capacity worked on this instance, it does not work on this instance. This is to say that a particular functional dependency may hold on some instances but not others. But it also tells us that room number is not enough to determine the capacity of a room. We also need building, the name of the building, to determine the capacity of a room. So really what we need is a functional dependency that says building and room number determine capacity. Here's another property of functional dependencies. If for a relation A determines B and B also determines C, we can infer that A determines C. This is just a transitive property in disguise, and it's one of several axioms that we call Armstrong's axioms. And then we get to an interesting property called closure. It's a closure, so closure is a property that you find in math and set theory. If a set is operated on by some operation and the result is another value in that set, then we say that that set is closed under that operation. So there are several ways to define the natural numbers, and one of them includes 0, so we're going to assume that 0 is a natural number. We can add and multiply any 2 natural numbers from this set as much as we want, and we will always get a natural number. So n is closed under addition and multiplication, but it is not closed under subtraction, because if we do 3 minus 2, we do get a natural number 1, but if we did 2 minus 3, we get a negative number. So n is not closed under subtraction, but if we introduce a new set, z, that is the set of all positive and negative integers, now it's closed under subtraction. So if we do 2 minus 3 on z, if we do 2 minus 3 on any 2, if we do 2 minus 3, the result is another number in z. If we did 3 minus 2, that result is also in z. So z is closed under addition and subtraction. And multiplication. But not division. We need a new set called Q for that. So Q is defined as the ratios between A and B such that A and B are in Z and B is not 0. Z is not closed under division, but it is closed, but Q is closed under division. You may have never seen this property before, and if this was the case, well, now you know what closure means. Given a set of functional dependencies F, F plus is the closure of F. That's the set of all functional dependencies that we can infer from F. So F is a set of functional dependencies. F plus F plus is a set of all functional dependencies that we can infer from F. So if we can infer a functional dependency from F, it belongs in F plus. There's another normal form called Boyce-Codd normal form, BCNF. This is considered more desirable than first normal form because it eliminates redundancies that we might find from functional dependencies. So here's the formal definition of that. A relation schema R is in BCNF with respect to a set of functional dependencies if for all functional dependencies in F plus of the form alpha determines beta, where alpha and beta are subsets of R, at least one of these holds true. A determines B is a trivial functional dependency, and alpha and beta. Alpha determines beta is a trivial functional dependency, and or alpha is a superkey of R. So a relation schema is in B, C, and F if at least one of those two conditions hold. By extension, a database is in B, C, and F if each relation is in B, C, and F. So here's that definition again. Let's explore what it means for a schema to be in B, C, and F by looking at one schema that isn't in B, C, and F. So there is a functional dependency where department name determines the budget. But department name is not a superkey because that's not enough information to uniquely identify each row in this table. So when we decompose this, we find that this is a better normal form. We find that these two relations are better than having the one combined relation because both of these are in B, C, and F. Both ID and department name are superkeys for their respective schemas. We can uniquely identify every instructor by their ID. We can uniquely identify every department by their department name. Also, we can also say that the ID determines the name, department name, and salary. But we can't say that the name determines the ID, department name, and salary because what if two instructors had the same name? We can say that the department name determines building and budget, but we can't say budget determines department name and budget. We can't say the building determines department name and budget because two different departments may be in the same building. So here's what you do if you have a schema that is not in BCNF. If this is the case, then there is at least one non-trivial dependency, alpha determines beta, where alpha is not a superkey of R. We can replace R with two schemas. The first one is A union B. Alpha union beta, I should say. The second one is a set difference of R and the set difference of beta and alpha. If you decompose a schema this way, and the resulting schemas are not in BCNF, you can keep going until you get a set of schemas that are in BCNF. In the case of our instructor-department relation, the attributes for that schema are ID, name, salary, department name, building, and budget. Let's call it R. Each department name is associated with one building and one budget. So we said that the department name determines the budget, but it also determines the building. So let's just write that. So we have department name, alpha, and building and budget, beta. So, as we've seen, this combined instructor-department relation is not in BCNF. So here's the process for how we would create the two new schemas that are in BCNF. The first new set is the union of alpha and beta. There we go. Let's move that to the side. The second new schema is built on two set differences. The first set difference is beta minus alpha. So that is everything in beta that is not in alpha. everything in beta that is not in alpha. So building and budget are in beta, and they're also not in alpha. So beta minus alpha is just building and budget right here. Now we have to take the set difference of R and this. So the full second schema is everything in R that isn't in the first set difference. The first set difference has building and budget, so the second schema contains all attributes except building and budget. And there we go. We have our new schemas. This is for the instructor, and this is for the department. Instructor, department. And if you recall from the instructor and department relations, these are all the attributes for those two relations. By the way, there are a lot more normal forms than just first normal form and BCNF. But we're only gonna go about as far as third normal form and fourth normal form. Yeah, there's like nearly a dozen normal forms out there. So we have first normal form, and then we have Boy Scout normal form. We're gonna look next into third normal form, which begs the question, hey, where's second normal form? The textbook talks about that. But anyway, we're gonna look at a few more normal forms after this, but I am going to end the discussion here and leave that for next week. So yeah, we're gonna continue at chapter 8 next week. Alright, that's gonna be it for this video. If you have any questions, let me know, and that's gonna be it. See you next week.